Thanks for the invitation. It's a great workshop. So I will tell you a little bit about the lower bounds on adaptive security. So I'm from IST Austria. If you have never heard of it, that's this beautiful campus here in the forests by Vienna. So this talk is ongoing work with my students, Chetan, who is here, Karen, who actually made the technical lower bounds that I will tell about, and Michael Walter. And actually we started this entire discussion when Mohammed was visiting IST. So somebody was actually asking about lower bounds. We thought, okay, so if one person is interested in that, let's try to prove something. So concretely, we had like a quite successful ongoing agenda over the last years, proving upper bounds on adaptive security. And this was in particular this framework by Jafar Ghoni and lots of other authors. There are so many authors because it unified things that were already existing there. And this framework basically allows you to prove, for many interesting cases, that allows you to prove adaptive security. I will show one example. Just for kind of simple existing schemes, as opposed to coming up with dual encryption or like massive machinery that then allows you to do the reduction here. And sometimes if you have some kind of constraints and so on, you can actually give yes. But I think I have this microphone. It shouldn't matter.
That's for recording.
Oh, I see. Okay. Good. Okay, so this is the outline. So let me just start. So I will just use one example throughout this talk because this is the only example for which we have lower bounds, and this is going to be generalized selective decryption. So let me first define what generalized selective decryption is. It's a very natural problem. You start with the building block, which is an encryption scheme. It can be either public key or symmetric. Let's use symmetric encryption to start with. So just totally normal symmetric encryption scheme. What we require is that the key space is a subset of the message space. So we can encrypt keys for that. The system can encrypt its own keys. And then this game, this generalized selective decryption game, is defined as follows. So we have like an adversary and the challenger. We fix some security parameter for the underlying encryption scheme. And then we have some kind of number n of keys. Let's say in this case it would be 5 keys. So Kermit, what he does is he samples. So he's the challenger. He samples n keys for the symmetric encryption scheme. So he has them, and then they start playing the game. It goes as follows. The adversary can ask all kinds of queries. So you can just ask normal queries. Encrypt this message under key number 3, for example. Right? So normal encryption queries, why not? But he can also ask, now is the interesting thing, he can ask for encryptions of keys. So he can ask encrypt key number 3 under key number 1. Sorry, no. So encrypt 3.1 means encrypt key number 1 under key number 3. So the first index will be the key to use in the encryption scheme, and the second is the one that. And if the adversary does that, for illustration, we'll actually draw such a arrow, and this arrow will mean, this directed edge will mean that we have so the adversary asks for an encryption of this key under this key, right? So and then the adversary goes on and he queries. There is no restriction on these queries except one, no cycles. So the graph has to be cycle free. And the reason is we want to reduce it at the end of the day to the encryption scheme. And if we had cycles, we would at the very least have to assume some kind of cyclic security. We don't have that, so no cycles. He can also ask corrupt queries. So for example, I say, give me key K4, then he gets it. Then we make like a soccer ball to indicate that this key is corrupt. And at the end of the experiment, he can say, he can ask to be challenged. So then the adversary has to ask, say, send over a leaf that is not corrupted and that cannot be reached from a corrupted key. And then what he gets is, either the key or a random value, and he has to say which of the two is the case. That's generalized selective decryption. Why is it interesting? For example, so why do people care about this? It has some, at the end he outputs a guess bit and if, standard advantage. Why is it interesting? It has, nice applications. For example, one is multicast encryption. So let's say we have those 4 organizers who want to organize a workshop, and they want to have some kind of shared key so that they can talk with each other. So maybe the institute here provides everybody with like a random key. Then the institute also samples a few more keys, n-1 more keys, and kind of publishes those encryptions, right? It publishes an encryption under this key of this key and so on. Now, everybody, each of those organizers here can simply decrypt this key on the top, and they can use this key to, to chat, or the institute can send the encryption under this key to everyone, and everything is fine. So what do we gain here? So now assume what happens is, Yuval starts to prove upper bounds, and not only that, he does it while eating pineapple pizza in his AC room. Of course, that he's out, right? So that's beyond the line. So he's considered corrupt at this point. So they want to kick Yuval out of this entire game. So they have to kind of, the institute has to set up a new key. If everybody just would have an independent key, that's a lot of work. But if we have this nice, this nice structure here, what we can do is we can just kind of sample a new path that kind of replaces the corrupted path, and just kind of give out logarithmically many, whatever, linear in the depth, logarithmically many ciphertexts to kind of to encrypt those nodes on the path, and everybody, all the honest parties here can still play on. And we now even have a new free slot, so we can add another organizer if you want to.
We have a few words after.
Okay. And in fact, like this is symmetric encryption. If you do the public key encryption, then even, you don't even need a group manager or something who is trusted to kick people out. Even the group itself can do that. I think that's how this fancy, the key, how is it called? MLS, message layer, this new fancy generalizations of signal protocols and so on to many, many group members kind of function more or less. Okay, so we really would like to prove adaptive security of these things. So how do we prove selective security? I will show you a restricted case where the graph is even more. So you see, the topology of the graph is typically not totally arbitrary, as I showed in the general game before, but often it's kind of implied by the application what it can be. Right? It's in this game, it's very restricted. Maybe still, people can get corrupted adversarially and so on, but it's never going to be something fancy. It's always going to be like a graph like this. So I will look at the even more restricted graph, which has to be a path. And I will look at the path because I will prove a lower bound, so I can, use the simplest possible graph. And for lower bounds, that just makes the lower bound more interesting. And I will consider a weaker game, a selective game, first. That's not what we care about, but that's the kind of games for which we can actually prove bounds easily. So what do you mean by selective? It means that the adversary cannot just start the game, but he has to first kind of announce something. He has to commit to some moves that he will make during the game. What these moves are depends on the primitive you want to prove. For this particular primitive, I want the adversary to commit basically to the path. He will say, this is going to be, I will play this game with you, but at the end of the day, the leaf will be K2, and then it's going to be this path K3, K0, K1. Right? So he has to commit to this. Then he can play this game, and at the end of the day, we will get this graph here. In fact, we will either get this graph or we will get this graph, because remember, at the end of the day, he gets, he wants to get an encryption of K2, but this is the challenge. So if B equals 0, he gets actually this edge. If K equals 1, he gets this edge here. So he has to distinguish those two cases. Now, let me give an even slightly different representation, namely the edge graph of this graph, which will be much more convenient. So now every edge, every encryption is a node. And nodes are connected if this encrypts a node which is used to encrypt this node here. And I will use pebbles. So sometimes a node will be black or sometimes it will be white. And black means that when I encrypted to this node, I actually did not encrypt the key, but the independent random value. So for example, if the game looks like this, the graph, so the configuration will look like this. In this case, we will have a black pebble. So this is the real and the random game. But once we do this, we can also assume that the challenger maybe does weird things, not as specified in the game, but he kind of deviates. For example, maybe he's kind of crazy and he kind of, instead of giving an encryption of K0 on the K1, he actually also gives a random value. The configuration would look like this. Why do we define such configurations? Because what we know, what we guaranteed by this adversary, the selective adversary, we start with assuming it can break GSD, which means it can distinguish this configuration from this configuration with some advantage epsilon. So now we can consider a set of intermediate games. Right? So each of these games simply means here the Kermit would, for example, always answer, encrypt random things. We can consider a set of intermediate games. And what do we know? We know that if he can distinguish this from this with epsilon, he of course can distinguish two consecutive games with on average with advantage epsilon over 5. In particular, there exists some two consecutive games that he can distinguish with epsilon over 5. And what I claim is that we can use any adversary who can distinguish two consecutive hybrids, as shown here, with some advantage, let's say epsilon over 5, to actually break the underlying encryption scheme with the same advantage. And I will show you how this works. So there is something special about this intermediate hybrid. So there is, they're not just arbitrary, there is a rule. And the rule is as following. To get from one hybrid to the other one, I can only do one thing. I can put one pebble, and on top of that, or remove a pebble, put or remove a pebble, and on top of that, this pebble has to be placed on a node where the previous node is already pebbled. Right? So for example, I can put the node here because the previous one is pebbled. I can remove this one here because the previous is pebbled, and so on. So that's the rule of the game. Okay. So let's see how I kind of use this fact that this guy can distinguish those two hybrids with some advantage to break the underlying encryption scheme with the same advantage. So the game goes as follows. Kermit samples the keys that he needs locally, randomly, except for this one key, which is kind of the one, corresponds to the one node which kind of changes from these two hybrids, this one. This one he doesn't sample. And also for each black node, he also samples some random nodes. Then he kind of asks for the challenge of this encryption scheme. And what he asks for is, he asks, say, look, encrypt, so this is the black node, encrypt K3 and R for me. So depending on the challenge bit of this challenger for the encryption scheme, he would either get an encryption of K3 or an encryption of R. Right? So this is this challenge ciphertext. And he wants to tell which is which, and he wants to use this attacker on GSD for that. So what he does is, they play this game, but when the attacker asks for an encryption of this key under this key, he simply sends him the challenge ciphertext. What does it mean? If the challenge ciphertext encrypts K3, so if the challenge bit here is 0, this corresponds to this hybrid here, right? He kind of encrypts everything correctly except this one black node. On the other hand, if the challenge bit is 1, we are in this hybrid below. And we assume that he can distinguish those two things with some advantage, so we can break the encryption scheme with the same advantage. Okay, that's a simple selective, selective reduction. Now, we don't care about, arguably, adversaries are not nice. They're not going to tell you how they're going to attack you. The point is, of this GSD game is we want to kind of be prepared for all kind of adaptive or unforeseen behavior of this adversary. So then the attack, of course, doesn't work. So where do we need the fact that he commits to this graph? We need it because otherwise it's not even well defined what it means to kind of play this or this hybrid and embed something there. We have to know where the keys are to put the pebbles at the right. Otherwise, it's not even defined. It doesn't make sense, right? We don't need this selective thing for the extreme hybrids. For this one and this one, here we don't need them. But for everything in between, we have to know where to put stuff. Okay. Now, there is like a nice generic statement, which tells you that whenever you have that we can always turn such an adaptive attack with, that whenever we are given an adaptive attacker, which has sub-advantage epsilon, we can always kind of just take it and turn it into a selective attacker, but we pay for that. And what do we pay? If the adaptive attacker has advantage epsilon, the selective one has much lower advantage epsilon divided by this size of this set W, and the set W is simply the set of possible commitments that we require the adversary to provide so that we can actually simulate those hybrids. So in this case that I showed you before, this set W is massive. It's kind of n factorial because we have to kind of give the entire path of these n keys and say in which order they come. So instead of losing something like in the game before where we roughly lost a factor 2n because we had 2n hybrids, now we lose 2n times n factorial. It's terrible, right? So how does this reduction go from this simple reduction from adaptive to selective? Now, he wished this guy was selective, but he isn't. So what he does is he just guesses it himself. Then he plays the game with the adversary. And whenever at the end, or maybe even during the game, if it becomes clear that the adversary does not obey his guess, that he kind of does something different than what he guessed, the reduction just aborts. And only in the rare cases, in the 1 over W cases where the guess is consistent with what this adversary does, at the end, he actually uses this output as his final output. You can do the math, that's going to work out. So this is just what I said. It's just a slightly more general statement. Whenever we have like a primitive, some indistinguishability-based primitive capital pi, like generalized selective decryption, and we want to reduce it to the security of a building block like the symmetric encryption scheme, then epsilon security of the building block will imply epsilon times m times size of W adaptive security of the more interesting primitive, so much worse, whenever those things are true, right? So whenever the games are connected by M hybrid games, we can simulate each hybrid game given the commitment from this set W, and moreover, any distinguisher for 2 consecutive hybrids can be used to break the underlying primitive with the same advantage. So now, in this framework of Giafragoni et al. From Crypto 17, we show that sometimes one can do much better, and the framework is very generic. What does it mean sometimes? It means whenever to simulate the hybrid, we maybe do not need this entire W. This W allows us to simulate each and every hybrid, each of these G0 to Gn hybrids. But maybe for intermediate hybrids, for each individual hybrid, we can use much, much less information. Maybe instead of a string of length 1,000, we just need like a string of length 100. And this framework basically tells you whenever you have that property, you get you can show that the loss is not exponential in the size of this set W, but instead just in the set of this much smaller set, right? So for every hybrid GI, we can somehow compress this witness, and you can use a different compression for each hybrid to something much shorter U, and then the loss is only exponential in this U. So how does this help? So this is interesting, of course, if U is much smaller than B. How does it help us? So for the hybrids that I showed you before, from the real to the random game, it doesn't really help, right? Because I don't see how to compress, for example, this configuration, because you have to put pebbles on half of the node. So you kind of basically have to tell for each key, I need at least one bit of information. Is there a pebble or not? That's not it's better than n factorial, but it's still 2 to the n. But you know, there actually exist better pebbling strategies. There exist strategies that are kind of recursive. You can put the pebble on, you know, I'm not going into it, but instead of using n pebbles, you can actually do it with log n plus 1 pebble. And it's a recursive thing, right? So you basically put the pebble here, then you kind of you keep it, then you use another, then you put the pebble here, then you unpebble this one, and you know, by doubling the number of nodes, you just need 1 pebble more. The number of hybrids grows, but not to bot, like to something like 3 to the log n, which is polynomial. Okay. So if you use this sequence of hybrids, you immediately, instead of losing n factorial, you only lose something like n to the log n. Because you can encode each and every configuration using only log square and bits. You know, this is a key. I need log n bits to tell you where this pebble is, and there are at most log n of them. So, you know, slightly super polynomial, n to the log n. Okay, but the question is, can we do even better than n to the log n, right? Because yeah. Okay, I'm coming to lower bounds in 1 minute.
The fact that the hybrid looks nice, like don't they allow you to compress the description? Like
Yeah.
Your hybrid, right? I mean, you have the tables.
Yeah.
So this restricts the number of configurations, right?
Yeah.
So can't you save using this fact?
No. So I mean, you can.
You have to encode it, but I'm just saying that the space of all possible things is not really like that large, because you know that you came from the previous state, right? So take into account
You could maybe save a little bit more because you know that, but it's still going to be exponential. Maybe another factor 2 or something. Yeah. You can get smart, but you know this is really so this is logarithmic versus linear. So okay, can we do even better? So just to recap, why we thought we can do much better, right? So what we did before is we had like this pebbling from the real to the random game, like this intermediate hybrids, and then we kind of, the adversary, so the reduction basically tried to hit one of those configurations. It had only log n pebbles, but still, right? And it just kind of randomly placed those pebbles somewhere, and maybe it placed them slightly wrong. Maybe it got to this configuration here, and in this case, the reduction would simply give up, right? But you know, maybe you could kind of think, have a more kind of a multiverse view. You think of playing many games, you think of having many paths, slightly different configurations, and you kind of, whenever you hit some configuration, you just look if it's on one of the paths, and then you think, oh, I actually was playing on that path from the beginning, right? So those paths will overlap at the beginning and the end because there are a few pebbles, but if the adversary has advantage on few pebbles, he should be, we can use, we have much better advantage anyway, and like in the fat middle, we should do much better. So this was kind of the hand-wavy argument why we thought maybe we can do much better. So but what I'm going to show you, maybe you can do a bit better, but not much. In particular, all the types of reductions that I showed you so far will never give you anything better than n to the log n over 2, so like a factor 2 in the exponent. So that's in the last 12 minutes or so, I show you how to prove this lower bound. Now I'm lower. It's like more than 1/3 of the talk. Okay, so what do we have? We have this reduction and we have this adversary. And this, this adversary must break GSD, and this reduction would like to use this adversary to kind of distinguish the underlying encryption scheme, right? So this is the game. This adversary reduction gets some kind of challenge, and they play this GSD game, and at the end he gets this bit B, and he wants to use this bit B from the adversary to somehow make some bit B for for his game. So at the end of the game, when they play it, they have a configuration which I assume looks something like this. It's like before. It has black and white pebbles, encryptions of real and random, and there's going to be potentially a gray pebble. What is the gray pebble? That is where the reduction embedded the challenge. So I assume this reduction is slightly black box. It does not crazy things like homomorphically add encryptions or something. It just embeds the challenge somewhere. So then, right, and embeds somewhere. And the other are either correctly encrypted or black means simply wrongly encrypted. Something like so. Okay. So I have to specify now an adversary such that it's going to be hard to kind of use this kind of, this bit here to distinguish the case where this point is gray or white. So how do I specify an adversary? I can think of the final configurations of the adversary or of this game as this hypergraph, right? There are edges of this hypergraph, which means that an edge means here that I can go from here to here by putting the challenge somewhere, and depending on whether the challenge is real or random, I will kind of be either here or here. That's kind of the thing, right? And the guarantees we have from the adversary is that he must output, let's say, 0 here and 1 here, or with epsilon, with probability epsilon, but let's say he's always outputs 1 here, right? So this is the constraint on the adversary. So, and I can define this adversary. So how will I define this adversary? I will somehow define a cut in this hypergraph, and I will say everything on this part of the hypergraph outputs 1, everything on that part of the hypergraph outputs 0. And then I know that, I call a node good if by putting one black pebble on it, I can actually pass this cut. Why not, right? Because now I can say this answer from this reduction will be useful for the reduction if and only if the configuration that we got, assuming this gray pebble was white, is on the is a good node. That because that it gets over the cut. That's clear. Okay. So this is not a good configuration because this would get us from here to here, but this would be a good configuration because this goes over the cut. Drawing cuts is very hard. I know you should think of a cut. Okay. So to prove a lower bound, what we must do is we must kind of define a cut and then argue that this reduction will kind of have hard time kind of finding a good node in that cut. So here is the definition of the cut that we will use. We will say, I will define the cut in terms of the good configurations. That's kind of implicitly then defines the cut. And I say that the configuration is good if the following is true. If this configuration contains exactly log n pebbles, I assume n is a power of 2. Log n pebbles. Remember, I can always go from the real to random with log n plus 1. So it contains 1 pebble less than is absolutely necessary to go from real to random. But this is not enough. On top of that, this configuration itself must be reachable with log n pebble. Or equivalently, because this pebbling is reversible, giving this configuration, I can get to the empty configuration without using any additional pebbles. And I claim, okay, let's see. What do we know? So for example, here, this is a good configuration. It has 3 log n, this is 8 log 8 is 3, so this has 3 pebbles. I can reach it. These are good configuration. This is not a good configuration. It has 3 pebbles, but you need 4 pebbles to reach it, because at this point here, you have that kind of 4. And you can show that you actually always need 4, right? Because to put the pebble here, you need 4. Okay. Okay, so what one can prove is if I put the pebbles at random, some log n pebbles at random on this path, I will end up in a good configuration with very low probability, something like this is exactly as n to the minus log n over 2. Why is this the case? Because typically what will happen if I throw them at random, there will be like a space, in most of the cases there will be a spacing between any 2 pebbles. But if there is a space between any 2 pebbles, I can't do nothing, I'm stuck. If I don't have additional pebbles, I can't remove a pebble, or and then it's okay. Maybe I'm lucky there are 2 pebbles next to each other. Then I can actually remove this one. But then I can only continue doing anything interesting if there are 2 other pebbles which are very close, namely if only 1 pebble in between. So you can put it in there and then remove those 2. And then you need like a configuration. Then you're stuck unless there is a configuration which has like a window of 4 and so on. So then you can, yes?
Can the reduction do rewinding?
Maybe. Okay, fair, good point. I think this is really not considered. I will come with other caveats. So, this is very preliminary. We don't have much. Because you see, I will. Yeah.
In the rewinding doesn't help. For example, the very first example that Krzysztof gave, that's how you need to guess the whole path. No matter how many times you rewind the adversary, it's not going to help you that much.
Yeah. So I think there was some reason why it's difficult, I remember, but I would have to think about it. Yeah, but okay, let's look at the restricted type of reductions now, and I will say this reduction is oblivious if it actually randomly places the nodes. What does it mean randomly? It kind of at the beginning says I will either put the pebbles on this and this and this and this key, or on random keys, or at random queries. It doesn't matter, but it should be the case that at the end of the day it gets a random configuration. And if the reduction is oblivious, then this fact up here immediately gives you that that every oblivious reduction must lose this n to the minus log n over 2 factor, right? So this is an observation. So the question is now, I'm almost done with the talk. Let's see, 2 more minutes. Okay, so now the problem. So the framework and also kind of this more general idea with the many fat paths and so on, this is all oblivious. So this shows us that that's a no-go. So this is, but there is hope here, right? Because, okay, maybe rewinding gives you something, but being non-oblivious might help you a little bit. And we have no idea how to do non-oblivious reduction. Somehow this guy kind of looks what queries he got and cleverly tries to kind of put pebbles depending on the topology of the graph. In fact, if he's not oblivious, then you can show that for the particular cut that I showed you before, you can actually hit it because you will kind of put the pebble somewhere, and then you will kind of connect components that are small and have pebbles on them, and you will actually have a good chance of hitting a good configuration. So there might be something very interesting there that you can get much below non-oblivious reductions, but we don't know how to do non-oblivious reduction. Simply, okay.
So you can consider this question into a clean question about the two-party game and pebbling game where you have an adversary.
Yeah, exactly. It's a very clean game, right? At this point, it's really kind of adversary, and if this one party is kind of oblivious, it's kind of a pebble. No, it doesn't even look at the queries. We know what to do. But the other thing is, yeah, the one party has to define a cut, and then it has to make it very hard for the other party to hit it. It's a very clean game, yeah. Open problems. Exactly, I mentioned. Is this non-oblivious? Is this a thing, or did we just kind of define a not very good cut? So I only showed it to you on the graph, which is okay, but the lower bound we can even hope to prove for a graph is at most the upper bound, which is n to the log n, but we don't have any better lower bounds even if the graph is complete, whereas then the upper bound is exponential. So can we do something there? Somehow it's very weird that it's not kind of easier or trivial to prove anything here. And of course, this framework has been used for a bunch of applications, right? So garbling, computational secret sharing, constrained PRFs, proxy re-encryption, all these things. Can you prove lower bounds on these reductions for interesting cases? That's actually it. Thanks for your attention.